Welcome to Brain Vision.
Right, so we need to show that the charged particle moving in the uniform electric field and uniform magnetic field shown in this graph would follow a cycloidal path. So if we want to show this rigorously, we need to solve the equation of motion for both x and y and show that they satisfy the cycloidal equation. But for this problem, we only need to do it qualitatively. So initially, the particle is at rest, so the electric field would give a change of velocity along the positive y direction. And using the right-hand rule, we can show that initially the Lorentz force points towards the positive x direction. Since the Lorentz force is always perpendicular to the direction of velocity, it will slowly rotate the direction of the velocity clockwise. And as the particle moves upward along the y direction, the velocity would increases. And as the velocity increases, the magnitude of the Lorentz force increases. So the curvature of radius would slowly increase. And when the direction of the velocity has rotated 90 degrees, the charged particle would at its highest point and then it will slowly move downward. And when it hits the x-axis, the velocity would become 0 again because the x-axis is the equipotential surface for the electric field, and the Lorentz force doesn't do any work on the charged particle. So when the particle hits the x-axis, the velocity gets 0 again, and the whole motion starts again, so it's a repetitive motion. Right, now for part B, we need to prove that the speed at any point is equal to this form. So let's assume that we want to find out the speed at point xy. And let's use conservation of energy or work energy theorem. So let's use work energy theorem. So the kinetic energy at this point minus the initial kinetic energy, let's say we choose this to be at the origin, equals the work done by the electric field, the work done by the electric force, and the work done by the Lorentz force equals 0 because it's always perpendicular to the velocity. And the work done by the electric field is simply Q times E times Y. So from this simple equation, we get the speed equals 2QEY divided by m, taking the square root. And for part C, we need to apply Newton's second at the top point to show that the speed at this point is 2E over b. So at the top point, Lorentz force minus the electric force should be supporting the center seeking force. So this should be mv squared divided by the curvature radius. So it's given in the question, which is 2y. And the magnitude of Lorentz force is just QVB. And for the right-hand side, we can re-express this using the result we get from part B. So mv squared over 2y is simply m over 2y times so the right hand side is simply QE. So from this equation we get VB equals 2E. So V equals 2E over B.